Thank you, sir. Respected Chair, honored veterans, ladies and gentlemen. Uh, as the previous session, my chair also was putting pressure on me that you got only 17 minutes to finish the talk. So I told him, sir, no problem. As it is, my talk is going to be hypersonic. So not to worry on that count, sir. Uh, Today we are going to touch upon something which is termed as a blackout of aviation today, and so you'll find most of my slides are dark indeed. Uh, could we have the your remote is not okay. Let me just check. All right. So 27th October 2021 is what we saw. Mark Miller's U.S. Joint Chief of Staff statement in the press. What we saw was a very significant event of a test of a hypersonic weapon system, and it is very concerning. I don't know if it's quite a Sputnik moment, but I think it's very close to that. It's a very significant technological event that occurred, and it has all our attention. We all know what a Sputnik moment is. Well, he was referring to a Chinese launch into space, which the Chinese have quite denied. They said, it was just a ordinary launch, nothing to get so excited about it. And what they probably launched was what is known as a fractional orbital bombardment system. It's not new. The Soviet Union deployed a similar system called the R360 well over 20 years during the Cold War. And it is something, as you can see from the slide on the right, instead of a ballistic missile which goes up as much as 1400 kilometers to its apogee, you will find that a fractional orbital system, something like a launch of a satellite, goes around the Earth. But since there is an understanding that we will not put weapons into an orbit, so the fractional orbital system, so that means we are going to use only a fraction of that orbit. And in this kind of a system, actually you can attack from this side of the Earth and you can go around the full side and launch. But since the terminal things are not sorted out, it's fairly inaccurate. So it's really opened up the debate. After 27th October, every day there'll be 2 articles in the newspaper on hypersonics. And people are asking, has the US really fallen back technologically so much? Or is just pure hype created for allotment of additional funds? Or is the US creating an arms race, which it knows it will win in the long run? And there are other people asking, or is the US just panicking and making the whole world more chaotic and threatening as ever? Well, let's look at the hype over the hypersonic. The word hypersonic, today when we talk, is like cutting edge connotation to it, and recent media coverages of it has treated the realm of hypersonic flight as it's right out of a science fiction movie. The truth is, however, that hypersonic platforms have been in some shape or the other since the 1950s. In fact, before that, the German V2, the X-15, a standard ICBM goes to Mach 15, a space shuttle go to Mach 25 during the re-entry phase. So these platforms have been touching that realm. It's not new. However, let's cut through the hype and now look at hypersonics at a very basic level. We'll start from the basic and then work up. When we say hypersonic, everyone says, Mach 5. Why Mach 5? It is an arbitrary figure because at that point, the air becomes or starts transforming into plasma. And that can happen slightly before Mach 5. It can go after Mach 5. So it is where the plasma effects need to be considered when we are considering aerodynamics. That is what is actually definition of hypersonic. Structural heating takes place significantly high. I will tell you how much high, especially at the leading edges. The aerodynamic environment is not fully understood in that realm. Whether the hypersonic boundary layers, the leading edge physics, the unsteady flow, it's messy out there. And incidentally, the hypersonic platforms have to maneuver in all phases of flight, right from, say, okay, not taxi, but right from launch, subsonic, supersonic, higher supersonic, lower hypersonic, higher hypersonic. So you're looking at control physics in an entire realm. And to support this, you need to have novel propulsion systems, which low speed, low height, high speed, high altitude. So there's quite a spectrum to be looked at. So let me sum it up very simply. You're flying under extraordinary conditions, extreme velocities, extreme forces, and extreme temperatures. This is a very unforgiving realm with very little margins. Small change, big impact. You do a small change into the control surface, the impact could be into a shock wave resulting, which you don't know where it came from. So it is these big impacts which need to be captured before we move on to testing any new platform. Okay, there are essentially, when now we are looking at not the civil flights of hypersonics, we are looking at the military side, where two approaches being followed. One is the what we call the boost glide weapons, which are accelerated high speed with some sort of rocket booster, perhaps even an existing missile booster like the Agni, and then coast unpowered simply from their own momentum. So you launch it, comes down, goes up, comes down, a bobbing and weaving effect, and you take this hypersonic glide weapon through to its destination. And the second approach, which is that is a hypersonic cruise vehicle. Now, these have engines, the scramjets that we've been talking about, that use oxygen from the air and produce thrust during the flight, just as other aircraft do. The first one, the glide weapons, is a simpler one. And most of the research, Russia, China, they have been into the glide weapons. It's the second one where we are looking at the scramjet technology integrating with the platform technology. That is a more complex one. Just to give you just a relative idea, the blue line is showing a typical ballistic missile. The apogee goes up to as much as 1,200 kilometers. The hypersonic glide weapon weaving between, starting from about 100 kilometers, weaving down to 40 kilometers onto the target, and the hypersonic cruise missile staying just below 30 kilometers. Okay, now developing a relevant hypersonic system is not easy. Air can no longer be assumed to be air. All our theories that we pick up during the subsonic, the supersonic can be thrown out of the window, and there are dozens and dozens of paper, and a lot of them in conflict with each other. So to sift through that kind of aerodynamics, because the nature of air has changed. The boundary layer transition from laminar to turbulent flow significantly affects drag, heating, and stability. And the flight envelope is where thermodynamics is probably more important than aerodynamics, because leading edge temperatures are expected to reach 2000 degrees centigrade, while titanium itself melts at 1700 degrees centigrade. So that kind of gives you an idea of what is the envelope we are looking at. Pressure rises across shock waves are similar to detonations, unpredictable, and interact with the boundary layer. The control devices have to be revolutionary. Standard control devices are not going to work. You may have to use thrusters, you may have to use a mix of standard control devices and thrusters. And everything is happening far, far too quickly. And optimization and integration of the airframes have to be thermally managed. The airframe cooling has to be done all around. And it's a very complex integrated design process and flight architectures that we're looking at. It's not only the platform, it's the engines. Scramjet propulsion systems, they need to compress, disassemble, mix, react, and exert thrust in only a few milliseconds. And someone has very, very nicely put it, it's like keeping a match lit in a hurricane. That's the best analogy someone could come across. Testing a hypersonic a vehicle is not easy either. One part is retrieving data. That part they have been overcoming to a great extent. However, more importantly, since creating the analogous conditions on ground is almost impossible, validation and verification of performance through specialized wind tunnels and flight testing is very difficult and arduous. Aerodynamic engineering, as it is not an exact science, but hypersonic field is far too assumptive and far too empirical at times, making it extremely difficult. But why hypersonics? Why? Why are we now so pressed about it? What does it change really in the operational domain? First is lower trajectory, less warning time. Second, maneuverability in the atmosphere. You launch something, you're at high speed. Okay, the missile is coming from one particular city, Alpha. Last minute, he says, okay, change to Bravo. All air defenses have to, adjust according to that. So that is the kind of maneuverability and the flexibility it offers to the military planner. And a reduced cross section is what is achieved. So it enables you to project strike power at greater ranges without falling victim to increasingly sophisticated defenses, essentially compresses the shooter to target window. And the fourth dimension warfare, the time warfare, comes into play. And this is going to have a huge impact on the enemy air defense capabilities, which also will need to get revolutionized. Now, you got a platform coming in at 12 Mach or 15 Mach, and you have to intercept it. If you go kinetic, you need to have something which is faster than that, or you got to go for laser guns. Now, how do you pick it up? Can your ground-based radars pick it up, or you need to have space-based sensors? Now, that is the future which is going to unfold and unroll. This is a very simplistic diagram. Low and Sneaky does it. Now, everyone says, why ICBMs could do it? Yes, they have been doing it all along. But if you look at this figure, a ballistic missile which is coming on a ballistic trajectory is predictable and can be picked up at far greater ranges. And as you can see, a hypersonic is picked up far lesser. Simplistic, low and sneaky. But now this is the proponents of hypersonics are saying, but there's a whole lot of critics and skeptics who says, if we introduce terminal maneuver capability into a ballistic missile itself, well, the same effect can be achieved. And current ballistic missile defenses are, as it is, far from perfect. The superpowers depend primarily on nuclear deterrence to dissuade rather than defend against nuclear attack from perceived foes and threats. There's another thought that we introduce countermeasures on existing ballistic missiles to increase their op efficacy. And all of these defense penetration techniques would also be available to hypersonic gliders in their terminal dive, but there's no reason to think that the gliders would be more effective simply because they got to the target area slightly faster than a ballistic trajectory. Radar cross-section reduction, yes, but that will occur only at particular frequencies, and most modern radars now today can operate over a band of frequencies. Given the design, very little leeway to accommodate stealth measures into hypersonics. Terminal intelligence, navigation, and control is the biggest challenge. We all know the Chinese program. Yes, they say, okay, anti-access, anti-denial, you come into a region, South China Sea, we will target your flotilla ships, but the terminal intelligence, nav, and control is still need to be sorted out. And even hypersonic missiles will have to decelerate below Mach 10 to 12 to reduce their plasma envelopes so that the external nav signals, the GPS or any other system that we have, can get through. Apart from the technical challenges all over the world, there are project management challenges to this because there is so much happening as it is on the subsonic side, on the supersonic side. that amount of funding that you need to start a new disruptive technology is really not available. So the policymakers and industry leaders really need to know what is happening on this domain. The test facilities, once again, need to be really, really revamped. Capabilities, techniques, and the analytical methods that we look at hypersonics, it's a quantum jump and a quantum change. Calls for close collaboration between various research labs, engineering institutions, and the industry. We had, a talk on the LCA, and the speaker, clearly brought out that just for an LCA, how many people, how many institutions, just for the design itself within the country have been contributing. This requires far, far more involvement of many, many high-tech companies, high-tech institutions and laboratories to contribute to it. And recognition by the government is vital, as significant capital investments required for running a sustained program with very long lead lines and no returns in the immediate. International hypersonic programs all over, are the cause of panic, worry, or concern? This continues to be debated. Quick geoscan on what's happening around. The pace of research towards weaponization has picked up early in the last 1 decade. Why so? There has been a stagnancy in the economy and arms market, and you need something disruptive, something new. The last change happened when huge amount of digitization took place. And that happened 25 years back. The markets awakened, once again, something new to excite. There's been a multifold increase in computational capabilities. Now that enables testing to a much greater extent, and the material sciences advancements which have taken place. The USA, Russia, and China obviously led the way. Incidentally, the US had a $2 billion budget for supporting its hypersonic programs 2 years back. They have now increased it to 3.8 or 4 billion in the current session. India, Australia, UK, France, and Israel, and North Korea also claim, have also invested in this. But when we read, when we research, we find that hypersonic information is always either covered with hype for political reasons or underplayed to lay claims for additional funding, which is happening in the US case at this moment. And each leader in the field terms the other contenders as call to action catalysts. So precise capabilities of hypersonic missiles and vehicles generally remains uncertain and controversial. We are aware of the names that we hear today, the Avangard, the Kinzhal, Triskon. The Russian mainly actually really not hypersonic stuff. Yes, they go hypersonic, but not the kind that we are talking about. They are kind of like a first stage of a ballistic missile and suitable sensors. So they claim, so they're making the right noise politically that we got hypersonic, but they're really not there. The US, once again, they are the ones who are underplaying it at the moment. The China with the DF-17, okay, we got your carrier groups in sight, still not there.
Just a couple of minutes, huh?
Pardon, sir?
Just a couple of minutes, I hope.
Just 5 minutes. So where are we and where are we heading? Well, all three nations, that is the US, China, and Russia, report testing. No one has yet conquered the environmental challenge sufficiently for reliable and successful maneuverable flight with precision targeting. That is the bottom line as of today. That such a capability will be achieved in the next decade, I am very confident that it will be achieved. So we are on the path. As of now, we don't have. And the introduction of artificial intelligence and loss of human control over decision making is inevitable, and it is going to come when it gets linked to hypersonic technology. But the key thing really is when we talk about warhead and target ambiguity leading to nuclear instability, the risk that a defending nation aware of an enemy's hypersonic launch and having no time to assess the warhead type or target will assume the worst and launch its own nuclear weapons. This is what is bugging the planners all over the world when it comes to hypersonics. Quick one on the Indian hypersonic program. We have the what is called the HSTDV, Hypersonic Technology Demonstrated Vehicle. Important milestone. There's no doubt in 2020. But what are we doing really? We put a kind of a scramjet engine on an ugly missile booster, launched it. The scramjet worked for about 22 seconds, and it does put us on the hypersonic map, but it's still not clear what exactly will be the application of this technology and the roadmap. But frankly, I've been researching into this topic. I personally feel that we should have invested more into the research for a boosted glide weapon at this stage, which is a simpler technology. Coming onto the scramjet technology, yes, it can be done parallelly, but let's first master the simpler one and then progress onto the scramjet. So that is a personal view. On the civil flight, a lot of startups have started coming and talking about this, but I say it is going to be some distance away, because safety and testing will be a chief concern when it comes to this. As I wind up, there's a very nice phrase that you see. Hypersonic flight is only 3 years away and will always be. Hypersonic initiatives over the past few decades have shown great promise. However, the sporadic occurrence of programs has hindered attaining desired capabilities in an efficient, rapid fashion. Every time a program ends, teams disperse, knowledge is lost, and new efforts must begin from scratch to regain momentum. Future efforts will only succeed if executed with consistent policy guidance, stable tech specs, and dependable funding streams. This is the lament all over the world. Thank you very much. I hope I've met your time frame, sir. Thank you, sir.
Thank you, Horax. One of the most difficult jobs is to contain the